So I'll just start right in. As Rachel said, I'm a senior geologist, technical specialist with the Reading office of the Central Valley Regional Water Quality Control Board. Can you hear me okay? Okay, great. And my job essentially is to enforce the Port Code, the Water Quality Control Act, which means translated that I permit and enforce on dischargers, that's corporate entities, who discharge waste to the waters of the state, and I do groundwater. I'm a hydrogeologist. So what I'm going to do tonight is, this evening, I'm going to do some case examples for interest's sake, but before we do that, I thought we'd do a little bit of pertinent background. And the main, so to start, what I'd like to do is go over the overall driving force for pollution that's increasing pollutant loads and demands on groundwater. We'll start at the beginning, okay? So, all right. So let's, and also what I'm going to do is, the way I like to do this thing so you don't get bored silly is I'm going to fire a lot of questions at you, so be ready, okay? All right. So let's first talk about population, okay? And I live in Reading, all right? And typical towns in the Northern Valley have a doubling time of about 50 years, okay? Right. So let's say Reading's population right now is exactly 90,000. This is just for illustration's sake, all right? The population is going to increase about 1.4% annually, and the demands on the environment are going to likewise increase. That increases exponential. Okay? So we're going to do a little bit of the math, and then we're going to talk about the politics behind the math. Okay? All right, so this is sort of like what you do for a checking account. Same kind of deal. All right? Okay. So you've probably seen this before a million times, but let's do it. Okay, so we're going to get to 180,000 and start with 90,000, that's 2. So 2 equals e to the kt, and t is 50 years. How many political administrations is 50 years, do you suppose? 4 years. 12 and a half political administrations, right? For the Board of Supervisors. Now keep that in mind, all right? So we're going to solve this out, and ln of 2 is about 0.7. So that's how I got my 1.4% annual increase. And the key take-home message is right there, yeah? Not that noticeable in any given year. Okay, so we start with 90,000, so that means in the first year, taking out your calculator, you get 1,260 people moving there, and then you add it together, you get 91,260, and then you add them together to another 1.4% compounded, you get 92,538 in year 3, etc., etc. So by N50, you're out to 180,000. All right, and again, not that noticeable in any given year. So let's say I want to talk to a board of supervisors about a sanitary sewer connection or something like that, and they're a very fiscally responsible board, and they want to demonstrate. They've got money to apportion out to different needs, parks, fire, police. Do you need an improvement bond to worry about something 50 years out? Yes. So my question to you is, how does this, now that I've led you down the garden path a little bit, how does this affect city planning and politics? Any comments?
Usually it affects it.
Depends on what the political views of the new this new population are.
Absolutely.
If they're liberal or conservative, or if they are.
Yeah. So since it's politically motivated, I think you're right. Since it's incrementally political, so you might have a forward-thinking liberal group in charge when there's a lot of financial largesse, and then the money gets tight, and then they throw the bums out of office and they get somebody else in. while all this is going on, this is creepy crawling along, so by the time year 50 pops up, all of a sudden, whoa, we're double in size, and all of a sudden, uh-oh, we don't have the capacity of the infrastructure. All right, big surprise, right? Any other comments or anything of note? It's pretty straightforward. We're not, big point I'm trying to get across is we're not famous for long-range planning. Okay?
How did you come up with 50?
It's just that I just played with my calculator, looked at population statistics, and also Perry Rand's textbook, Applied Engineering Geology. He does this in the beginning chapter 2. That's not like that. Okay, so these are some interesting numbers. This is U.S. per capita statistics, gallons per day per person. So yes, the average person uses more gasoline than drinks water during the day. Is that a good thing? No. Okay, and wastewater, that's a combination of gray water and black water. So pretty amazing, right? Okay. So where I got these numbers, in case you're interested, that's the what is that I got? McClellan Financial Publications. This is US EPA, and this is a textbook by Kreitz and Chabanagos on decentralized wastewater. It's kind of a standard text on wastewater. All right? And then it's much more difficult to quantify. It's certainly somewhat a function of increasing population, but less meaningful in these terms, gallons per day per person, are per capita use of, say, chlorinated solvents, pesticides, herbicides, others. For example, good point source, common one you studied on in class is tetrachloroethene, or PCE. You read about it commonly in contaminant journals. May have correlated in some fashion to populations generally function. You use it commonly in dry cleaners, aerospace, heavy equipment manufacture. All right. So while we're going on this subject, I'm not going to go into urban runoff or any related issues. I'm going to strictly stick with groundwater at this talk. All right. So now we're going to get into groundwater. All right. So what I'm going to do is I'm going to do some essential concepts in groundwater flow, pollutant transport, and movement of or threats or impacts to pumping wells. All right? Groundwater, pollutant transport, and threats and impacts to pumping wells. Okay, and then when I have you set up to that point, then we can go into case examples. All right? Good enough?
Yes.
All right. So this map is courtesy of the Department of Water Resources, and it shows the shallow hydraulic gradient, right? The red arrows. Hydraulic gradient, is that the same thing as the direction of groundwater flow? Yes or no? Who said no? Who said no? You're right. Yeah, it is not. Hydraulic gradient is not the same thing as the direction of groundwater flow. The direction of groundwater flow is a combination of the hydraulic gradient and the direction of maximum permeability, okay, in the aquifer sediments, all right, and which dominates. The direction of maximum permeability dominates, okay? That's actually pretty important. So let's take a look at this map really quick and what might control the direction of groundwater flow. On the west side of the valley over here, you see these channels over here? They parallel the gravel bars and very big stream deposits all up in here. They trend basically from southwest to northeast, mainly like that. How do I know that? The Franciscan Formation outcrops along here, and it has a distinctive wine red chert in it, and when you cut cores over here, you find it. So it's just that simple. And you can see on aerial photographs from the valley, you see them running like that. Although, look here, I've got a gradient going the other way. So the true direction of groundwater flow in here might be a bit different. Down the center of the valley, the groundwater has gotten out of the higher part of the Tehama Formation, which is what I was talking about, and gotten into some younger gravels and sands associated with the Holocene from the valley here. And on this side of the valley, there's a tectonics, right, the Chico monocline, and they have tilted the post-ion sediments, and that's where your shallowest groundwater is, and say the Modesto Formation. Who in here are not geologists that I'm just going to whoom? Okay, okay. Bottom line, again, direction of groundwater flow.
I understand that.
Yeah. Okay, cool. All right. All right. Now, what I want to cover. So these numbers are total heads in wells. What do I mean by a total head? Total head. Okay, I'll draw your picture. So, ground level, a well with a perforated interval in it, and a static water level in it, over a datum, which is sea level. So we'll go for the midpoint of the screen interval. From there up, that's elevation head. And from here up, that's pressure head. Added together, total head. Okay? Right? So, pressure head. Everybody go like this. Mo from side. Bad. Okay. So pressure head is psi, which equals water pressure over rho g. These are constants. I sure hope so. So then the numerator is pressure, water pressure. So can I have a negative? Can I have a negative water pressure? Can I have a negative water pressure? Where would I have a negative water pressure?
Above the water table.
Ah, right, above the water table. Right, very good. Okay. So far so good. Too rudimentary, right on target, too advanced. Right,
Yes.
okay. Lay off the Greek, okay? Okay. All right, next question. So we talked about Vadal zone. If the total head were down here in the screen, what's that mean? Is it hydraulically confined or unconfined? Unconfined. So if it's up here, it's hydraulically confined, which means translated, I got a gravel down here and I got a big clay on top, and the pressure head is pumping the level up above the clay, so it's hydraulically confined, right? Okay? So good? All right. Next. Okay. This is kind of important right here. This is Darcy's Law. I could draw you another picture if you want. Can you see this in the dark okay?
Yeah.
All right. Why not? Can I erase? Good?
Yeah.
There won't be a test. This is kind of a classic, so I'll just do it. Again, we got a datum. I'm going to have a cylinder and a really smart hydraulic engineer from France named Darcy. Yeah. Okay. Q in, Q out, and there you go. And got an angle theta. If I can draw it nice. Is the flow a function of theta?
Yes.
No? No. Doesn't matter how I orient the cylinder. It's not. I can twist it in space. Not a function of angle. Okay? Stand around its head, move it to its side. Not a function of theta. Okay? I got myself two manometers sticking up in there. I got a water level here. the water level here, the difference, change in head. I do the calculus, it comes down to a slope at a point d of head, and we have this distance down here over distance. dx. All right. So if I stuff this pipe full of gravel versus if I stuff this pipe full of silt, what would it do to that? Gravel, silt, less or more. It's kind of like resistance to electric current. And okay, if this was filled with gravel, this would be small. Or if this was filled with silt, it'd be great. Yes? Darcy's Law. Okay. Now, back to Darcy's Law. Here we are. Big Q equals hydraulic conductivity times gradient times area of the end of the cylinder. Okay, well that's no good. That's not good for us. We're going to divide through by A, and we're going to get little q. And that is what we call a volumetric flux. It's not a true velocity because it's still related to a volume. But we still use it all the time as if it were on maps. But always remember, it's always still really tied to a volume. Okay? Now, I'm going to divide my little q by effective porosity, and that's your seepage velocity, right? Now, what's the difference between effective porosity and total porosity?
Specific attention.
Mm-hmm. Specific attention. What's an example of a sediment where they're about the same? How about a box of bowling balls? Okay? Or ping pong balls, right? A box of billiard balls, really nice. Yeah. So you let all the water drain out of there, and pretty much shake it up and then it'll come out. Okay? If you've got little dead ends down in there, then your effective porosity is a whole lot less than your total. So like, let's say I got a clay. The total porosity of a clay is very high. It could be 50, 60%. How about the effective porosity of the clay? Very low, right? Okay. How about a diatomite? Light as a feather. How about a piece of pumice? Light as a feather. Couldn't push water through it on a dare. Right? High total porosity, low effective porosity. It's like in a piece of scoria, basaltic rock. It's all a bunch of little vesicles, a bunch of bubbles with glassy ground mass in between. Couldn't squish the water through on a dare. Right? A sand, the way to think about it, if you've got grains, right, I'm going to have lithostatic pressure and hydrostatic pressure. Lithostatic pressure is the weight of the earth, and the hydrostatic pressure is the water pressure inside. So if I have a sand, then the weight of the earth is taken up by the grain-to-grain contact, so I can flow water through the holes in the middle. So the hydrostatic pressure is less than the lithostatic pressure. In a clay, they're the same. I stamp on it, the water can't go. Lithostatic pressure is the same as hydrostatic pressure. Got it? Good? Good. Okay. Now, here's an interesting one. Note this equation here. What if my effective porosity is really, really small? What happens to my seepage velocity? All right. So let's say I had a clay, and I had really contaminated, like say I got a clay liner in a landfill, and I got horrible ghastly leachate above the liner, and I got a little pinhole in the clay. How fast is that water going to come through the little hole? Like a fissure in it. Like lightning.
Yeah. Leaking down.
That's why you got to compact those things really good before you bury them over. You don't want to have a breach. Okay? Now, what if I have no matrix porosity at all? What is fractured bedrock? Can I still use Darcy's Law? Yes, but it's scale dependent. I wouldn't want to use it like one little incremental fracture, but if I consider like a whole basin, right? But the more tightly I look at it, the more of a lie it would be. Okay? So far, so good? All right. So, far off the deep end they went. Okay, now we're going to talk a little bit about contaminant, or pollutant transport. I say pollutant because I work for the water board, and we have a definition for pollutant. A lot of people use contaminant and pollutant interchangeably. It's my job, that's why I said pollutant. Okay, here we go. Okay, now we're going to talk about two very fundamental equations of organic pollutants. What's an organic pollutant?
Carbon.
Okay, it's an organic compound that's at a concentration that is either pollution or nuisance.
Animal waste.
Could be. Well, nitrate is not an organic pollutant. How about benzene or gasoline? How about trichloroethene, TCE, pentachlorophenol, things like that. Okay? That's an organic pollutant. Okay? Good enough?
Yes.
Okay? Right. All right. So when you have the structural formula of an organic pollutant is going to control how much it absorbs. So the way to think about it, you've got a lot of dipole in the molecule, right? Charge on one end, the positive and negative on the other. Kind of, I like to speak in analogies. Let's say I'm sitting in a canoe in a river, and I'm flowing along with the speed of the river. Then I get off to the bank, and there's a bunch of sweepers overhead. And I stick my paddle up kind of weakly. And I kind of poke up the branches harder. Then I'm going to go ever slower and slower with respect to the water retardation. Okay, so let's look at the first equation right here. This is the concentration of a pollutant, of organic pollutant in the soil. We're going to do that in micrograms per kilogram usually. And then this is the equilibrium concentration in portable water, and that's going to be in micrograms per liter. So usually this number here, the distribution coefficient, is in liters per kilogram in most textbooks. Okay? And this number in turn equals this guy right here, organic carbon coefficient, and this number right here is called FOC, or fractional organic carbon. Okay? So the charge, the sweepers over the channel, they're the naturally occurring carbon in the soil that want to grab your molecule and not let them go. Okay? So the structural formula will govern how hard the particle, the soil must hang on to that and not let it go. All right? So let's do some examples. MTBE, you've heard of that? Methyl terpiolate ether, made all the papers for many years. It's like oxygenated gasoline. It has a KOC value of 14. Another component of gasoline, benzene, it has a KOC of 58.9. And then perchloroethene has a KOC value of 155. All right? Now, a FOC value typical of a silt or a clay might be, say, 0.005. This is a rational number, unitless. And of a sand, a lot lower, like 0.0005. So, how might that relationship affect an aquifer cleanup? Okay, so the lower the KD, does it want to be more in water or more in the soil? The lower the KD, since this is a ratio, the lower that number, does it want to be in pure water or in the soil?
Water.
Water. It wants to be in water. So MTBE, with its lowest KD number, it really wants to be in the water. PCE, it hangs back. It wants to be in the soil a little bit more. Okay? Everybody clear on that? All right? So this is the double-edged sword of this. It's like, for example, this is a core of a silt, laminated silt from coin. And if I had PCE bound up in some of that, I tried an active cleanup method. I couldn't get it out of that for love or money, right? But then again, on the other side of the coin, it's not going anywhere very fast. So that's kind of a management call. Everybody see that? It's toxic, it's really bad for you, but if I'm confident that I know the subsurface conditions, it might just sit down there like a lump till the end of time, in which case I can manage it versus making them come out and do something that's not cost effective. So it's the management part of it, all right? And then my job is to go, look, I know you're complaining a lot here, but I know you can't afford that, and these are the numbers I need. The stringency depends on the case, and also how close the nearest receptors are, but this is a very fundamental relationship. Okay? Now let's look at the second equation. The only term here, that is the dry bulk density of the soil, all right? And that is usually ranged from 1.5 to 1.9 grams per cubic centimeter, all right? So you're going to notice in here that this is how slow the groundwater flows, how slow the pollutant flows relative to the flow of groundwater. Clear enough? So we've seen all these terms so far, and there's nothing surprising yet, right? Okay?
That unitless?
Yes, that is unitless. So if it had a retardation factor of unity of 1, it'd be something like MTBE, which really wants to go. It's got a very low KOC value and relates back down to here. PCE, it's going to be a lot less than 1. Okay? Everybody see that? You good? All right. Okay. Now we're armed with these so far. Let's say I have a monitoring well and I got a pollutant in it. I can look at the retardation factor, the Darcy flux, we talked about a little cube, and groundwater flow direction, and the site history to try to figure out how far upgrading the pollutant might have come from. How would I do that? I'd run it back up gradient and go how far could it have come from, right? Like for example, PCE. They started using it in the United States as an industrial solvent in the 1930s, right? Then they really got crazy with it in World War II, including for aerospace. And then in the Cold War, really used a lot of it, right? So that might give you a sense of the maximum concentration and the timing of it, okay? Now what are the limitations of such a ballpark estimate? Remember back to our groundwater gradient now, right? It's a question of scale, is what I'm getting at. The farther up gradient you go, the thinner the ice you're walking on in terms of credibility. Because if you might be in the same sand body for about 1,000 feet up, you're going to start going, to 4 or 5 different sand bodies. You might cross over a buried fault or an unconformity. The more the geology changes as you go back up gradient, the more shaky ground your case is on. It could bothering somebody about how they're supposed to pollute out in that well. All right. So the farther they outstep, the more the extraordinary claim, requiring the extraordinary proof. Okay. Simple enough. So far. All right.
Is that physically the gradient itself that creates more potential, creates more probability?
Yeah, but there's another component that we haven't gotten to yet. It's sort of like, I'll give you a preview. This is sort of like, it's like throwing a ball. The concentration's like, either Clayton Kershaw or a little leaguer, right? The higher the concentration, it's like, bam! Versus low concentration, little toss. We'll get to that in a minute. Okay? It's going to go much farther.
Thanks for the baseball, that was good.
All right. Turn the Giants side, got that.
Right. Yeah, go A's.
Sorry. I'm a Giants fan. All right, now the next thing we're going to talk about is pollutant biodegradation. All right? This kind of behaves like that compounded interest equation backwards that we showed you at the beginning of the talk. Okay? All right, so this is time minus the log of the goal concentration over the start concentration divided by, what's that? That's a constant, a rate constant. It's a rate constant, okay? Now, the goal, in my case, would be our water quality objective, our numerical water quality objective. Like, for example, PCE is 0.06 micrograms per liter. That's a goal. I have to go, what's the goal? Can I ever get there? All right? All right. So, what you're doing here, typically what we do to analyze these things, realistically, if we have groundwater monitoring wells, we'll plot the concentrations as a function of over distance, and look at the slope, we plot the natural log of the concentration over a distance, and look at the slope, and that's the slope. And that, I believe, is just the little cube. Okay? The paper is here if you want the reference. I'll get it to you later. All right? And that's basically what we're looking at. So, conceptually, if I look at this slope, and over time, the slope steepens, is that a good thing or a bad thing? Good thing. That's a good thing. It means it's crapping out a lot shorter distance from the source. It means biodegradation is happening. The bugs are taking it down, usually. If the slope remains reasonably steady, is that a good thing or a bad thing? The short answer is it depends. Okay? The slope flattens, is that a good thing or a bad thing? That's a bad thing. We don't want to see that slope flatten. We do not want to see that at all. That means the plume's surging. Something happening. All right? So, for petroleum constituent, say benzene, aerobic bacteria tend to, they metabolize it very quickly. And then facultative bacteria, they're a little slower, and anaerobic bacteria, they're the slowest. Okay? So we measure the petroleum pollutants, we usually look at it in terms of they're called electron acceptors. We'll look at the dissolved oxygen, and then there's usually sulfate in the groundwater. I'll go from sulfate to sulfide, and then finally we'll look at CO2 and methane. So usually you'll have an anaerobic core, where you have anaerobic bacteria, a facultative zone, and an aerobic zone. And that's usually what goes on with petroleum. Chlorinated solvents, that's an interesting thing. Like, you've heard of PC, right? And it goes from PC to TC to cis-1,2-DC to vinyl chloride. Okay, that's a co-metabolitic reaction. And usually the anaerobic bacteria, in fact, there's this one dude you want to find. His name is Dehalocoquates. The other Dehalobacters will run you partway and die. Dehalocoquates is the guy you want to find who will run you all the way to vinyl chloride. All right? And that all happens anaerobically. They have another substrate, another food, and they breathe the chlorinated solvents. Weirdly enough. Okay? And it's serial first order decay. So this becomes a lot more complicated with the chlorinated solvent side. All right? So, this is an interesting thing about PCE. I told you before in the last bit that the retardation factor of PCE was pretty high. How much is, what's the molecular weight of chlorine? Yeah,
35.
That's a lot, huh? You got carbon, he's 12, you got hydrogen, he's 1. You got 4 chlorines in a PCE. Tear one of those dudes off and replace it for a hydrogen, what happens to the molecular weight? Whee! And went to Jenny Craig. All right. Tear off 2. Whee! Tear off 3. He's really going to go. And that's a problem because PC is very toxic, and vinyl chloride at the other end is very toxic too. But fortunately, once you get vinyl chloride, if you get back to aerobic conditions, then it mineralizes very quickly. But when you manage the cycle, you have to keep that in mind. So overall, we kind of went through this before the implications of this chart. So if I was regulating a site like that, how would I use something like this to manage or regulate a site? Kind of what are the primary considerations? Any comments? Hint: don't let this get in somebody's well. Okay? How about gradient direction? That's important. The long axis of the plume, how well is that mapped? Because this presupposes this nice, believable lake slipper sort of shape. Means I'm confident all my monitoring wells are the same sand body, they're not spanning different ones, they're the same degree of confinement or unconfinement. And I have this mapped out well enough that I believe it. Okay? I'm never going to be able to afford, hundreds and hundreds of monitoring wells to map the whole thing. Do I believe it well enough? That's the fundamental question. What's that aiming toward? If I have somebody's well sitting right there, well, then I gotta really watch the slope part. This is out in the middle of nowhere, where I can just tell the county, just make really sure you don't have any well permits in here that haven't looked at, and we haven't talked to. You manage it that way, but that's the general idea. Got it? Okay, and then it also depends on, also that governs the degree of rigor we require cleanup on. Okay? So again, if you look at this equation, the throwing the ball analogy, the higher the source, the more this is going to poke out, right? There's your plume length, it's a function of time, and it's definitely a function of that ratio. Cool? All right. Now, pollutant dispersion. I'm not going to, in this class, I brought a bunch of stuff with me, but I don't want to run us out of time real quick. Basically, the dispersion is a function of longitudinal dispersion, transverse dispersion. Usually that's 10% of that one, and that's 10% of the total plume length. What's the rest of it? It's called a vector transport. So basically I'm taking a boxcar groundwater and moving it down gradient. So how far does it stick out ahead? That number. Very important, they're scale dependent. Okay? How am I doing on time? Do I gotta move it along?
We've got 10 minutes.
Great. Okay, and I'll burn through this really fast. Okay, what I want to show you that's essential. All right. We went to that. Went through that. Okay, now we're talking about the throwing the ball analogy, so the higher the peak, the greater it sticks out. No big surprises there. Okay? And one of the things about the highest concentration, it's the most important and the least well known. Just by common sense reasoning, if I have a plume down there, what's the chances that I'm going to drop that drill bit right through the worst of it?
0.
What if I have somebody who's got something to hide? Or functionally from my gas station, and I know the leak came out of the dispenser, below the dispenser island, and they got a big aluminum canopy over it, and nearest I can get. You know, I know it's higher, but my wells are I just can't get the rig in there. All right? And I don't want to have a monitoring well in there and get somebody run over every 3 months either, right? So there's practical considerations, but usually the C0's the least known parameter. Okay? And I think I'll go through that. One point on this before I move on is I'm assuming that the pollutants behave conservatively when I look at dispersion. What do I mean by that? They're non-reactive and they don't biodegrade. Okay? Like nitrate. Once ammonia goes to nitrite to nitrate, once that happens in the subsurface, it's going to stay nitrate. And it's miscible in water. So dispersion is very good, amenable to looking at nitrate transport. Okay? Okay, now I'm going to do flow to well really quick. This assumes continuous pumping. There's your well. This is at the well, X is 0. This is the pumping out of the well. Hydraulic conductivity, you've seen that before. That's aquifer thickness. That's hydraulic gradient. Okay? And this distance here is this little distance here down to the well. And this is the maximum width out here of a parabola. All right? These equations are very commonly used, like, for example, in the wellhead protection program. These sets of equations assume perfect hydraulic confinement, no leaky aquatards, and continuous pumping. How often do I have that in reality?
Hardly ever.
Thank you. If I had a polluted municipal well, would I keep pumping on it and give it to everybody? No. Okay. So what's a soul do? All right. Well, this is a good first cut. This is a very good system of equations to use for designing a remediation system when you are continuously pumping. But when you get a real world problem, this is pretty bare bones. Okay? Let's see what else I want to cover in that. Okay, one thing before I get off this though. If I'm a particle of water and I'm here, just outside the envelope and coming along here, whoop, what's my well doing? pitched it around like a sidearm. My well has accelerated the pollution. So when you design a remediation system, the well spacing is very important. You don't want to have them too far apart, it can make matters worse.
Can you
Okay.
explain what the axes are here?
Okay, this is map view, this is groundwater, I'm sorry, this is plan. So you're looking straight down at it, that's direction of groundwater flow, that's traversed. Okay? So, unrealistically simple. Also that gradient right there is high, that's ambient gradient, that's not pumping gradient. Okay? Again, perfect hydraulic confinement, continuous pumping. Alright? Never happened. This is what's used with a pumping well, okay? This is the Cooper and Jacob equation. It's an old guard, very simple equation, okay? And this is drawdown in the well. This is a conversion factor for getting into gallons per foot squared. This is transmissivity, which you've seen before, K times B, okay? And this is the pumping radius, and this is a number called storativity, all right? Which is very closely aligned. Actually, in a confined condition, this is just the amount of water the formation will give you by a grain rotation. It's small. Yeah, and an unconfined aquifer is close to effective porosity. It's how much water would drain out under gravity. And their confined conditions is a very small number. All right, now, we looked at well logs from drillers' logs from, okay, they're usually really detailed descriptions of the subsurface stratigraphy. You've got every single bed down there, and you can go down and estimate how thick the units are. And no.
If they came through our program.
Very good. Okay. But if I went to your mortals files, what do? I do that. I take the pumping rate, divided by the drawdown times this conversion factor, and it's close to T. Okay? That's a useful thing. So in absence of good stratigraphic information, I gotta do things like that, but that's a pretty useful little arrangement. All right? Now we can get on with our business here. Okay, now I've gotten you this far. Very quickly, this is a wastewater lagoon. It's in Shasta County, and back over here I've got a landfill. So let's say, for argument's sake, that somewhere out over here I got an angry well owner who's got nitrate in his well, and he says, these guys did it or these guys did it. How would I approach the problem? Knowing what you know now, what would I do first?
Just the hydraulic gradient, see which way it goes.
Sure. And then after that, throwing the ball over Clayton Kershaw or Little Leaguer. Maximum concentration, right? And then what usually happens out in the, is this guy, if he's living out there, is he near city services? No. That's why he's on a well. What else has he got?
Septic.
Right. So he might be facing the enemy, and it is him. Okay. So I first inventory the sources. I look at the overall hydrogeology. What else do I do?
Like samples?
Yeah, I review the files. If these are permitted facilities in our agency, there's groundwater monitoring wells out here. I'll look at them. Okay. And then from there, I can do more exotic things. I will move on to the next one. Everybody kind of get it conceptually? Okay. Here's an interesting one. This is in Reading. I've got a well at this farmhouse back here, got MTB in it. We had to put him on piped water. Now, I got the ACID, the Anderson Cottonwood Irrigation District Canal right here. I have a sanitary sewer running down this street, and it's near grade to about there, and then it dives down about 12 feet and goes under the canal. I have bulk fueling plants I'm standing on, one up here. I got one here. I got one there, and I got one there. Who paid for that and why? Who paid for the hookup, the quality of the water, and how do we figure it out? Guesses?
Shared.
What would the deepest pockets?
We definitely found the guy.
Weakest orders.
I was able to uniquely go, you did it, you didn't, you didn't. What did I do?
Well, aren't there certain signatures and different organic compounds that you can trace back and determine the source?
That's a very good one. Here's a cool thing you can do. When you look at petroleum, there's this neat ratio. Benzene, toluene, and benzene xylenes. These two move quickly in groundwater, but they're biodegradable. These two don't move as quickly in groundwater, and bacteria don't like the flavor so much. It takes more energy to break the rings apart because they got more chandeliers sticking off the pipe. This here's like an easy pop top, ring fishing, no problem, C6H6. This is a little more complicated, but they can usually bust it out pretty quick. These fight a little bit. Now look at that ratio and the gradient. Helps you map it. Very good question.
Is that on Market Street?
Hmm?
Is that on Market Street?
Yeah.
I know that site.
Oh, okay. Next. Okay, this one's closer to home. Okay, this is the Jesse Lang site, the Kinder Morgan site in PG&E. Okay, this is what you call a site conceptual model. All right, and I have free product on the water table there and there. I have this monitoring well in Kinder Morgan, and it's got increasing MTBE in it. And according to this site conceptual model, the source of the MTBE was here. These blue lines are equipotential lines, and you'll notice that they're not at right angles to the water table. Why not? The cross section is vertically exaggerated. That's one part of it. All right. Another part of it is anisot. The only reason an equipotential line would meet the water table at right angle is that it's isotropic and homogeneous. A box of ping pong balls, which it is now. Okay. All right, so this is a companion conceptual site model saying that this well is a conduit that brought it down. How would I? So I have two working hypotheses how it got there, one or the other. What would I do to figure out which was which? Same kind of question. What data would I need to sort of put in more monitoring? Well, it looks like we got enough of them to figure out who done it. And what would I watch for? Any questions? Any ideas?
Break down how things break down and degrade over time, or how they trace back.
Yeah.
How long the source.
Oh, I like that. If MTBE converts to terpene alcohol, and what happens is that the carbon heavy isotope lags back. I'll give you another analogy about isotope geochemistry. I thought I'll make it quick. Okay, you've got a heavy-set middle-aged guy at Disneyland wearing the ears. And he's got 5 kids all wearing the ears. And they all want to go to the rides really bad. You know, come on, Dad, hurry it up. And they'll go, save me a spot in the line. You know, guys, I'll be right with you. And he's trying to catch up, and he gets on 80% of the rides, but he runs into various problems, so 20% of the time doesn't quite make it. One of the kids stays back to wait for Dad. Most of the time you get on the ride, and he doesn't get to go. Okay, so the reaction happens. It's just a little slower. He's pulling a couple extra neutrons over the years. Okay, so that's what happens. So you can look at the ratio of the heavy isotopes and the lighter ones. So MTB to TBA. TBA reacts way faster, so you just look at the residual, the carbon-13 heavy part. That's a very good one. Any other ideas? Since I'm running low, I'll pop in another one. Ooh, drama. Okay, this is up the Feather River Canyon, and this in 2007. There were 2 tanker cars. There's one of them right there. We spilled 30,000 gallons of ethanol, major ethanol, and 25,000 gallons of canola oil. The geotechnical aspects of this case were not inconsiderable. We lost buttressing and arching effects for the engineering geologists. It killed a lot of trees, and so the trees are trying to block it, and it's now got lubricated soil oil and all that. But let's concentrate on the hydrogeology aspects, the ethanol part. Okay. Right, so here's the extent of the ethanol. And down, this is all granitoid bedrock, quartz, monzonite, granodiorite, what have you. Exfoliation fissures, that was the main fracture system that moves the shallowest groundwater. And down here is a terrace gravel about 40 feet thick, highly permeable, full of boulders and gravel and sand. And I got a well, domestic well right there, and he's the terrace gravel is about 40 feet thick. The sanitary seal of this well goes down to 20. Half of the open interval, the top part of the open interval is in the gravel, the rest of it's down in fractured bedrock. This well got hit with denaturants in the ethanol. You know what a denaturant is? They put the benzene, toluene, benzene, and xylenes in the ethanol, basically because they're about the same boiling temperature in ethanol, so you can't drink it without getting poisoned. That's what's denatured. Otherwise, they would have spilled gin, and everybody drinking out of the well. Okay? So, this gravel is highly permeable, but it never got in the river. Up here, we had explosive levels of methane coming up. What happened? Your body loves to metabolize ethanol, right? You don't feel very well in the morning, but it does it. Bacteria do the same thing, and they go anaerobic, and they make methane. So eventually pass it.
So you had a lot of drunk bacteria?
And dead bacteria, right. But since this groundwater is blowing through so quick, they keep getting replenished. And although this is very permeable, it never made it to the river. And that's probably why it didn't make it to the river. Bacteria eating it faster than it was discharging. All right. Active remediation, although we could get it to vaporize and put a soil vapor extraction system in, it didn't work with the hoop. Why not?
Too permeable.
Right. It would have taken a ridiculous amount of wells to do any good because the water's just getting out from under you too quickly. Okay? How much time I got left?
That's pretty much it.
Okay.
I would love for folks to have the opportunity to ask questions if we have any.
Okay. Hi.
Hi.